had to verify this service life by a probabilistic approach, and the limit state was that after 100 years only 10% risk is allowed for corrosion initiation. This project, at this project, COWI worked as the main consultant together with DEWO, who was the main contractor for the project. And here the input parameter for this durability modeling, you can see again the concrete cover, the chloride migration coefficient, the age factor, and so on. And here results, for example, for the bridge in the splash zone. The client required a probability of max 10%. This means a reliability factor of 1.3. This is the same for structural design, the correlation between probability and reliability. And for a given cover of 75 millimeter, this is about 2 inch, we can allow a maximum chloride migration coefficient of 3.5 to the minus 12 to achieve a service life of 100 years with this maximum reliability. Here are the results from the submerged zone. Due to poor practical reasons, the contractor wants to have the same cover in the splash and in the submerged zone. This means 75 millimeter or about 2 inches here. But in this case, we could allow a higher chloride migration coefficient because this is the less aggressive exposure zone, the underwater zone. And we did that. You can see that in this case we can allow a chloride migration coefficient of 6.5 to the minus 12. Sorry. And here this table shows the finally selected durability key parameter for the design. As I mentioned before, the contractor wants the same cover for the splash and the submerged zone, but we allowed a differentiation with regard to the chloride migration coefficient. And the next big step was now that the contractor has to convince us and the client that he can produce such a concrete with such a low chloride migration coefficient. I worked at this project for several months in South Korea together with the contractor, and we made a lot of trial mixes. About 50 trial mixes have been done, and we tested the chloride migration coefficient with this anti-build method here. And you can see some results from the pre-testing. On the left for Portland cement fly ash and microsilica, and on the right slag cement fly ash and silica. And actually this is unusual for Europe. In Europe we allow not this combination. We allow slag cement plus fly ash, but not in combination with microsilica. But it's allowed according to the Korean standards. And you can see that, have a look, that several mixes comply with the given requirements. We had 3.5, and for the tunnel we had a chloride migration coefficient of 6.5. And we tested this chloride migration with this anti-build method. This has been developed in Sweden and is now the standard test method for our durability design. And we require that in our specification for the pre-testing, for full scale and for production testing. And there has been made within also this research project and later on within COWI, we made a comparison of this different concrete durability testing. And I know that a lot of, in your country, it's usual to use this ASTM 1202. But actually this is, to our experience and to the experience of a lot of our clients, not a reliable test method. First of all, it's an indirect test method. You measure columns and you do not measure the chloride ingress. If I have a modeling for the service life, I also want to measure the ingress for the chloride. And therefore this is done actually with this rapid migration test method. It's a direct test where we actually model the decisive transport parameter, the ingress penetration of chlorides directly. This has been recognized in Europe for quite some years, and therefore, for example, the society, the British Concrete Society, recommends to use this rapid migration test as the compliance testing. Only as a replacement or as day-by-day construction control, I would say, you can use this one, but not as a compliance test to see whether the mix comply with the requirements given in the design. The next big project where we implemented the approach is the International Airport in Oman. In this case, the client required a service life of 50 years. Also in this case, chloride-induced corrosion was the decisive deterioration. And he made the durability modeling. And the big advantage using this model is that we can do this modeling for the different exposure zones the structural components are exposed to. We have done this here, for example, for the bridges, for the structures in the wet-dry zone, the most aggressive one, for the structures which are submerged, and for the structures which are exposed to the atmosphere. And you can see that we have a decent high chloride content in the groundwater. We have 22 kilograms per liter chlorides in the Baltic Sea, where we normally operating with in Denmark. We have about 4 kilograms per liter. The next project where we used it, and this is the most recent project where I was involved to use the approach, is the Qatar-Bahrain Causeway. It's a 40 kilometer long causeway, a segmental bridge, the longest in the world. The bridge is called the Bridge of Friendship. It was very challenging because, first of all, this bridge is lying in one of the most aggressive exposure zones in the world. We have extreme high temperatures, about 33 degrees, and we have a very high chloride content, about 6%. Normally we have only 2.2% in the Persian Gulf. It was also challenging for me as a female engineer, because it was not always easy to convince the Arabian client that an engineer from Europe could maybe do the design for the Middle East. But unfortunately, no. The client was very demanding and required a very extensive durability study. And you can see here the most recent guide to the design of concrete structures in the Arabian Gulf. It's a very good textbook which I can recommend also for you here in this area. It's the newest one which we have on the market, and it's from the Concrete Society. And in this guide they say that you should not use the ASTM 1202 method anymore, and they give a lot of explanation why. The durability study should include a definition of the exposure conditions. We had to elaborate different durability strategies, starting with black steel and a very thick cover over stainless steel, cathodic protection, prevention, and surface coating of concrete. And on top of it, we had to calculate the service life of these different strategies by using one of these models. It's actually was standard in the employer's requirement, and we used the FIP-Boyeting model here, or the Duracrete model. You can see there's some other models on the market, and you have used this Dura model here from Grace Dale, and there's this famous Live 365 which you can download, and a lot of engineers here in the United States using this model. But let me give you one remark. This has been financed by the Silica Association, and there was, of course, a commercial interest in it when they financed this program. And we did a lot of comparative studies using this model 365 and our model. And it's easy to say, you can only achieve a service life of 100 years if you use microsilica or corrosion inhibitors. And this cannot be the case. As we said and discussed yesterday, in our part of the world, it's not used. We do not recommend use corrosion inhibitors and so on. We are very skeptical about the long-term performance. And it must be possible to design a concrete structure without using microsilica corrosion inhibitors. And the other thing is you have to put these inhibitors in the bulk of the concrete. And you only need it at the concrete cover. So by using so much money for the bulk of the concrete, we should rather concentrate to make a good cover concrete. Yes, and I would like to show you some of the results. We also did some lifestyle costing, as we had mentioned, but unfortunately there was a heavy diplomatic dispute in May this year, and the project was suspended. But there is some hope. At the moment the King of Bahrain and the Emir of Qatar talk to each other again, and we believe that the project will be constructed soon, because too much money and too much prestige has been invested in this project. It cannot be cancelled. Yes, you might know, you said it, there will be a connection between Germany and Denmark. It's the Fehmarnbelt link, and it's about 20 kilometer length. And COWI has the job to make the best bridge solution, and our competitors, Rambo, has the job to make the best immersed hull solution. And at the beginning of next year, the client will presumably decide whether it will be a bridge or an immersed hull. Within our COWI group, we made some preliminary calculations for the concrete cover by using this dual grid approach. And we divided the bridges in the different exposure zones, which we have according to the Eurocode. We have an atmospheric zone, we have a zone exposed to the icing salt, we have a submerged zone, and a splash and tidal zone. And for all these different exposure zones, we calculated now the probability of corrosion depending on the cover depth and a certain type of cement or a binder. And you can see in that case you need at least 75 millimeters, about 2 inches, to fulfill the requirement of a probability of 10%. But this, please be aware of, that this is only valid for a certain type of cement or binder. It will be quite different when we're using other types of binders, because the chloride migration coefficient depends first of all on the cement or binder, and secondly on the water-cement ratio. For example, a Portland cement has a chloride migration coefficient of 10 to the minus 12, a poor Portland cement. A Portland cement with fly ash has about 4 to 5, only half. A slag cement has about 2. There's quite a difference in the chloride migration coefficient for the same water binder ratio. And this we can see here if we use other combination of cement. This is, for example, the blast furnace slag cement according to the European standards for concrete, for cement. We